Hi everyone, and welcome to the first of two videos going through some past exam questions on Hess's law. So Hess's law questions pretty much are always the same. They always look very similar. You get a little table with a few enthalpy changes in it and then a blank space, and it's usually worth about 3 marks. So you can kind of tell it's a Hess's law question just by looking at it. Okay. So what have we got here? This is the equation that we're trying to figure out. And the key thing in any Hess's law question is to look not really at what you're supposed to be working out, but at what information you've been given. This is the key. We've been given enthalpy changes of formation. Okay, we can see that it says delta HF. So if these are enthalpy changes of formation, they are the enthalpy changes for making these chemicals from their elements. So we can turn this into a cycle by having the elements here, and I could write them out, but I can't be bothered. But we can make these chemicals out of the elements, and we can make these chemicals out of the elements. Okay, so it's really important when you're drawing these Hess law cycles that you get these arrows the right way round. Okay, and the way that we know that the arrows are pointing upwards is because the information we've been given is enthalpy change of formation. So now we can match these numbers onto the diagram. So glucose here is minus 1250. There is no value for the oxygen because there's no such thing as the enthalpy change of formation of oxygen. You're forming oxygen from oxygen. There's no process. You're not doing anything. So because it's an element, you're forming it from its element, so there is nothing that you need to do. Here, the carbon dioxide is minus 394, but I'm going to need to times it by 6. And then I'm also going to have the minus 286 for the water, and that's also going to be times by 6. Okay, and so then what Hess's law says is that it doesn't matter which route you go by, as long as you start and you end up in the same place, then the enthalpy change will be the same. So if we just label these up, let's call this A, let's call this B and C. So hopefully you can see that if I start with my elements, I could either do B and then A, or I could do C, and I'd end up in the same place. So what that's telling me is that B plus A equals C. Yeah, if I'm starting here, I can go there and then there, or I could just go straight there. Okay, and either way, I've started and finished in the same place. So the one that I want to work out is A, so rearranging this, A must be C minus B. Okay, so let's calculate this then. So our enthalpy change, the one we're interested in, is going to be this. Okay, let's work this out. Let's just add that up first. So we've got minus 394 times 6. What have I done there? Minus 394 times 6. Minus 286 times 6. So that's minus 4080. So that is C. It's minus 4080. Minus B. So minus 1250. Okay. So we're going to add on 1250 essentially. Oh, I've just messed that up. Minus 4080 plus 1250. Yep, so we get minus 2830. And that is our value. Okay. Then we have here, suggest 2 reasons why standard enthalpy changes of combustion determined experimentally are less exothermic than the calculated theoretical values. Now, we saw a very similar question to this in the videos on 9.2, calculating the enthalpy changes. So it's the same kind of question coming up again. The problem with doing the experiment, okay, is that the definition for enthalpy of combustion, okay, enthalpy of combustion is when you have 1 mole of a compound and it's completely combusted. So if you ever get any incomplete combustion happening, that is going to mean that you end up with an incorrect value. And then the second point, because we're talking about standard enthalpy change of combustion, is if we do it under non-standard conditions. Okay, let's look at one more. So here, as I said, you get a very similar question. Hess's law questions always look the same. You get a little table with some enthalpy changes in it, and then you get a little blank space, and it's worth 3 marks. Right, so they're kind of predictable. They've just put a couple of extra questions in here for us to do first. So what is meant by standard enthalpy change of formation? So this is the enthalpy change that accompanies the formation of 1 mole of a compound. So that's the key bit. It's got to be 1 mole from its elements in their standard states. Okay, and then it says give the standard conditions. So we need to remember these. You need to remember the standard temperature, which is 298 Kelvin or 25 degrees C, and the standard pressure, which is 1 atmosphere, or you could do it in kilopascals, be 100 or 101 kilopascals. Okay, write the equation including the state symbols for the reaction that represents the standard enthalpy change of formation of this ammonium chlorate. So we need to do what we've just said. Okay, we need to show an equation that is forming 1 mole of a compound from its elements in their standard states. So I need to make 1 mole of this compound. We need to put the state symbols on. So then this must be from the element. So we've got the element nitrogen, which is N2. But I've only got 1 nitrogen in my product, so I'm going to have half a mole here. Hydrogen in elemental form is H2 gas. I've got 4 hydrogens, so that's going to have to be times by 2. Chlorine is Cl2 as a gas, and I've only got 1, so I need half a mole of that. And then oxygen is O2 as a gas, and I've got 4 of them, so I need to have 2 moles there. And there's my equation. Okay, so now we need to calculate the enthalpy of formation of NO using the data above. So this is where our Hess's law question comes in. So we are being asked to calculate the enthalpy change of formation of NO. Okay, so for this then, we need to be looking at this equation here. This is a bit of an awkward one because usually, you can probably hear me hesitating a bit there. Okay, so what we do is we'll write the enthalpy change of formation of NO across the top, and then we'll find some other reactions that add up to that. But that's not the reaction we've got. We've been given this, so we need to use this. Okay, so I'm going to copy this out again here. We've got 3Al plus, it's a bit of a horrible equation. O4. I'm going to leave off the state symbols because they're not really relevant. Plus 6H2O plus 3NO. And then remember, the key thing with any Hess's law question is to look at what information you've been given. These are enthalpy changes of formation. And so therefore, when we come to do our cycle, we need to have the arrows pointing upwards, okay, from the elements. Okay, and then we need to put the values from the table onto this diagram. So what have we got? The ammonium chlorate is minus 295, so that's here. So we've got minus 295 times 3. There's going to be no value for the aluminium because that's an element anyway. Okay, so that's it for that one. Then we've got the aluminium oxide, which is minus 1676. We've got aluminium chloride, which is minus 704. We've got 6H2O, so that's going to be minus 242 times 6. And then we've got 3 lots of the enthalpy of formation of NO, which they haven't told us, because that's what we're supposed to be working out, isn't it? So we're going to have plus 3NO here. Okay, and so that means they must have given us this value for us to be able to work this out. So this is the minus 2677 from up here. So that is here. Okay, this is a bit of an awkward one then, but we can do it through the same logic here. So we are looking for 2 roots that start in the same place and end in the same place. Remember, Hess's law says Doesn't matter how you get there, as long as you start and you end in the same place, you're fine. So let's call this A, let's call this B, let's call this C. And hopefully you can see I could start on my elements and I could do B and A, or I could do C, and that would start and end in the same place. Okay, so we're saying B plus A equals C. And then C is kind of the one we want to calculate because we want this. So let's put our numbers in here then. So let's work out 3 lots of minus 295 times 3. So that's going to be minus 885 plus, let's put these numbers in brackets, plus A, so plus minus 2677 is going to be equal to C, which is 3NO, and then all of this lot. So let's add this up. So we've got 242 times 6. Actually, let's do minus 242 times 6, minus 704, minus 1676. Okay. Minus 3832. Right, and now we just need to work this out. So if we add this and then add this to this side as well. So we've got, so you can see what I'm doing. So we've got minus 885, minus 2677. And then we're going to add on the 3832 from this side. So that leaves us with 270. Okay. So here we've got 270 is equal to 3 times the enthalpy of formation of NO. And so therefore the enthalpy change of formation of NO must be 90, which is dividing by 3. And it's going to be, that's a positive number, isn't it? So it must be plus 90. Okay, we always want to put a sign on an enthalpy change. So that's a bit of an unusual one. Don't get freaked out if the enthalpy change that you've been asked to calculate here is not the equation you've been given. Okay, always write the equation you've been given across the top of your Hess's law cycle. So you take that and write that across the top. And then remember the key thing was to look in the table and say we've got enthalpies of formation. So therefore this must be a cycle with the arrows pointing upwards. And then you just find your values and put them on, and you find, oh, I'm missing this one. So now I just need to rearrange an equation to calculate that one.